Hi Varun, good evening. Are you able to hear me? Yeah, good evening. So yesterday we have seen some of the chapters in this magnetic effects of electric current. Okay. So whatever we have learnt yesterday, we are going to have some revision. In addition to that, we are going to see some of the important questions in the exam perspective. Okay. Right. Now let us recall some of the points which I have learned yesterday. Right. Here the first question. In the beginning itself we have learnt about the magnetic compass and a bar magnet. Right. The question will be like this. Why does a compass needle get deflected when brought near a bar magnet? Right. So this is the question. So how to answer this question? Actually, we know that the magnetic compass also has got a small magnet which is pivoted. Pivoted means which is it's a hinge at the center, and also it is free to rotate. Okay. Now there are two magnets. One magnet here, small magnet, a bar magnet is there. Right. So when two magnets are there, naturally what will happen? There will be interaction between the two magnetic field. Right. So this magnet will have the influence on this magnetic compass. It will exert some magnetic force on the needle, compass, magnetic needle. So due to which what will happen? It will start deflecting. Okay, this is the reason why the magnetic compass is deflecting when it is brought near a bar magnet. Okay, so the main important concept is that both of them are magnet. But this is powerful magnet than this one, because this is a small magnet which can influence a little bit of magnetic field. But this bar magnet has got more magnetic power, isn't it? So due to which this bar magnet is exerting the magnetic field or magnetic force on this compass, due to which the compass needle, which is pivoted on the horizontal plane. You know that, suppose if it is a magnetic compass is kept like this is called a horizontal plane, right? It is kept on that. This compass needle is free to rotate about 360 degrees. Okay, so that is the important point you have to note down. And then the next one, the definition. After learning about this magnetic field, you have to define what is a magnetic field, isn't it? So the point is this one: the region surrounding a magnet in which the force of the magnet can be detected. The force of the magnet can be detected is said to have a magnetic field. This is the region around this magnet. How can the force due to this magnet can be felt? Can you tell me? How can you detect that magnetic field? How can you detect the magnetic field around the magnet? I said that this bar magnet is going to have a magnetic field around that. Can you tell me how can you detect it? I said that the region, the total region you have to tell me, the totally, to what extent this magnet can exert the force, magnetic field, isn't it? That region, total region, how can you detect that? There are two ways for detecting the magnetic field. We have learned yesterday. Can you just recall it? Exactly. The first one is by keeping the magnetic compass. To what extent the magnetic compass is showing deflection, that is the first method. Exactly. The second one is by using this iron fillings. By sprinkling the iron fillings around the magnet, the magnetic lines of force will be created. So these are the two methods by which you can detect the magnetic field around a magnet. Okay, so this may be another question, possible question. The next one, we have already learned that magnetic field is a vector quantity which has got both magnitude and a direction, isn't it? And the direction of the magnetic field is taken in which the north pole of the compass needle moves inside it. That we have learned by using a small magnetic compass we kept inside, in which direction the north pole is, the red point, pointer, the magnetic needle is there inside, the red pointer is showing, isn't it? So that is the conventional method to take the direction of the magnetic field, isn't it? So this is the another question. The next one, what are magnetic lines of force? Isn't it? This is also we have learnt. We have understood how to draw that and also how to detect it, but how to define it? This is the way to define it. The magnetic lines of force is an imaginary straight or curved path. It is imaginary straight or curved path along which the north pole of the compass needle moves in a magnetic field. If this is the magnetic field, you can see that this is the magnetic compass we have kept here, and the pointer, this is what the pointer, north pole of this magnetic needle is showing. So this is the imaginary curved or a straight path. Here we can see that it is only a curved path, but in this place where you can see here, or if it is a uniform magnetic field where there won't be any curved line, there will be only straight lines. So in that point, how it is moving, the north pole or the needle of the magnetic compass is moving in the magnetic field. That is nothing but the magnetic lines of force, isn't it? Okay, now here the properties, 3 properties which you have to remember. Can you remember that? Can you recollect what are the 3 properties of these magnetic lines of force you have seen? The first one is, yeah, tell me. The first one. Yes, exactly. They emerge from the north pole and merge or terminate at the south pole. But inside the magnet, it should be in the opposite direction. They start from the south pole and end in the north pole. This is the first property of the magnetic lines of force. Yeah. The second one, the magnetic lines of forces they are closed curves. By using these number of lines of force, or how close they are, the proximity we say, isn't it? The closeness or proximity of the field lines. This only will determine how strong is the magnetic field. That is the second point you have to remember. The magnetic field lines or closed curves, the relative strength of the magnetic field is shown by the degree of closeness of the field lines. So, what is the important point? The field lines are stronger where the field lines are crowded. They may give a diagram like this by drawing too many curves and one more diagram with a fewer curves. They may ask you which magnet is stronger. By looking at that, how many lines are there? By comparing the number of lines in both the magnet, we can say that which magnet is stronger. Right? If more number of magnetic lines are there, more number of field lines are there, or if they are very closer, then we can say that that magnet is much more stronger. And the third point, yesterday you asked me why any two magnetic lines of force intersect. They do not intersect, I said. No 2 field lines are found to cross each other, or they will never intersect, isn't it? This is the simple way to explain it, though I explained it in terms of magnetic field, because when you are talking about this one, this is the path along which the magnetic compass needle is moving, and if you take any 2 lines, they will never intersect. Suppose, imagine that they are intersecting at one point. It is not possible. Imagine that they are intersecting, right? At that point, if you keep the compass needle, what will happen? The compass needle should show 2 directions of the 2 lines which are intersecting. But is it possible for one compass needle to show 2 directions? Yeah, tell me. No, it's not practically possible. Since there is only one magnetic compass needle is the inside, which is not possible. So we say that, we assume that the field lines will never cross each other. Okay, this point you have to note down. This frequently they ask this question, and also which is somewhat concept based one. Okay, so we say that no two lines are found to cross each other. If they did, assume that they cross each other, it would mean that at the point of intersection, the compass needle would point towards two directions, which is not possible. Am I clear? Yeah. The next important concept which we skipped yesterday, because I thought that this is only for 12th standard, but you got this also, which is in 12th standard we call this as Maxwell's corkscrew rule. But here we call it as right hand thumb rule. Right hand thumb rule. Okay. So this rule is the one which helps us to understand the direction of magnetic lines of force. In which direction? If the current is flowing through a conductor, how to find out the direction of magnetic lines, magnetic field lines. Okay. So for that, the law is like that. Imagine that you are holding a current carrying straight conductor. Either it can be like thumbs up or thumbs down. Anyway, anyway you can keep the hand. Okay. Just to keep that, holding a pencil like this. You are holding a pencil like this, or some rod. That you are holding a current carrying straight conductor. Imagine that this is the current carrying conductor. Okay. In your right hand, not the left hand. I am showing a left hand because you can visualize this as right hand. So I am holding like this. So if you keep that in your right hand, what will happen? You are imagining that the thumb is pointing the direction of current. Okay. Imagine that you are holding a current carrying straight conductor in your right hand such that the thumb is pointing the direction of the current. Then the curling fingers, isn't it? The folded fingers which is wrapping the conductor is in the direction of field lines of the magnetic field. So whichever way you hold that, because in sometimes in the exams, they will simply point, instead of saying the direction, they will say that a conductor is held in your right hand such that the thumb is pointing out in the east direction, they will say. Okay, in the east direction. So you have to imagine that, you have to point out this finger in the east direction, then tell me whether the curling fingers are upward or downward. You have to imagine that. Okay, so always remember the concept, then you can keep that in any direction and then find out the direction of magnetic lines of force. This is how we have to apply this for different situations. Okay, are you clear about this one? This concept of right hand thumb rule. Clear? Yeah. Yeah. Actually, how this is otherwise called the Maxwell's corkscrew rule. See, though it is given as a note for you, but in 12th standard, if you go there, you will be studying as a Maxwell's corkscrew rule only. A corkscrew will be like this. It is something like, using a screwdriver, how will you nail a screw inside the wall? This is what it says. Okay, you can either hold a screwdriver or you can take this corkscrew, and if you start rotating that, what will happen? It will advance through that, isn't it? Using a screwdriver, if you start screwing a screw on a wall, as you screw the screwdriver, what will happen? The nail or the screw will advance inside, isn't it? So using that concept, they have defined the direction of magnetic field. How is it? Suppose if we consider ourselves driving a corkscrew in the direction of the current, okay, taking this, the corkscrew is the advancing in the forward direction, is the direction of current. Okay, then the direction of the corkscrew, in which way you are rotating, right? Which way you are rotating the corkscrew, that will give you the direction of the magnetic field. This is the other way of saying the right hand thumb rule. Is that clear? The only thing is how to put the statement properly, because these statements are actually given by great scientists. We should never interpret and give it in some other form. Is that clear? Suppose if you take Fleming's left hand rule, these rules, laws, everything should be reproduced as it is. We are not allowed to make any changes. Okay, if it is any descriptive type, we can make any changes according to our own convenience or knowledge. But these rules or laws should be written as it is. So just to try to grasp it. So if we consider ourselves driving a corkscrew in the direction of the current, then the direction of the corkscrew is the direction of the magnetic field. That is called the Maxwell's corkscrew rule. Okay. Now there is another question, board exam question. Yeah. Now a current through a horizontal power line. This is the horizontal power line. There is a power line here, cable. Right? A current is flowing in east-west direction. What is the direction of the magnetic field at point directly below it and at the point directly above it? What are they asking? The power cable is kept horizontal. The current is flowing through this. Right? And they are asking what is the direction of magnetic field above that and below that. Okay? So for which you have to always use this direction symbol in the exams also. Just put this symbol, put northwest, east, south. Just keep it ready so that when you are answering the question, you can readily refer that and give the answer correctly. Right now, what principle we have to apply for this? Can you just tell me? To find out the direction of magnetic field for this current flow, which rule we have to apply? Exactly, right hand thumb rule. So, since they say that the current is flowing from east to west, so this is the direction. Now, we have to keep the right hand this way. Okay? So, the thumb is pointing the direction of the current. So, just look at the diagram now. You can see here, this is the diagram. Now, I have kept the right hand thumb so that it is pointing from east to west. East to west. Okay. Now, what is the direction of the magnetic field? Above the rod, what is that? And below the rod, how is it? What happens? On both the side, it is same only actually. Right? We get the magnetic field above or below, right? In the same way, but how to view that? When it is viewed from one side, it may be looking like clockwise. When it is viewed from other side, it may be looking like anti-clockwise. Since they say that it is from east to west, we will start from east. So when you are seeing from this direction, from east direction, you can see that the magnetic lines of forces are, you see that this is the direction, isn't it? So the curling fingers are showing. So this is the direction. So what is this direction in the clock? It is in the anti-clockwise direction. You have to keep the clock like this and watch, visualize. So viewed from east direction or viewed from one direction, or we can say viewed from your left side. Okay, left side, it looks like anti-clockwise, or viewed from this side. Viewed from east side, what will happen? It will be on the other side. Suppose if I am viewing from this side, okay, what will happen? It may be looking like this one. What is this? This is anti-clockwise, and here it is clockwise. Is that clear now? Viewing from east, it is what direction it is? Yes, clockwise. So if it is viewed from west side, it is anti-clockwise. Yeah. So this is how we have to give the answer. Right. The next question. When we are talking about the magnetic field produced by current carrying wire, yeah. Tell me. Yes, please. See, they say that the current is flowing from east to west. This is the horizontal conductor. Okay. The current is flowing from east to west. So they are asking what is the direction of magnetic field lines above and below this conductor. This is the question. Okay. Now what we have to do, we are applying the thumb rule. Now when you are applying the thumb rule, it is nothing but you just have to keep the pencil or pen in the exams also, hold it and just keep the thumb finger like this. Now we can understand what is the direction of the current. Now here it is like this. isn't it? So when it is like this, when I am viewing from east direction, that is from east, from this direction, I can say that it is in the clockwise direction, isn't it? The finger is showing, the curved fingers are showing that it is in this direction. That means you have to keep the clock and see it is clockwise. Now similarly, when I am keeping the finger like this and view from here, what happened? It is going to the other direction. The fingers will show you it is in the opposite direction. Are you able to see that? If you can keep like this and see. So it is in the anti-clockwise direction. When it is viewed from this direction, you have to keep the finger and view from this direction. Have you got it? The only thing is, when you are keeping the hand here, right hand, and you can see that, visualize easily. But when you go to the other end, you cannot keep your hand and see from the other end. You can only ask somebody else to keep the hand and see from the other end. That is the difficulty here. Only thing is, you have to visualize. Imagine that you have left the hand here and come here and see. Okay? Right? The statement you have to give that properly. What is the question is that they are asking the magnetic field above and below. Whether it is above and below, both are same only. It is around the conductor. The magnetic lines of force are around the conductor. But we are specifying that how it is viewed from east or west, how it is looking, clockwise and anti-clockwise. Okay. The next point we have already learned that the magnetic field produced by a current carrying wire at a given point is directly depending upon the current through that, isn't it? So if more current is there, more amount of magnetic field. So how can you increase the current? Either by increasing the current, or you can increase the number of turns. If the coil has got n number of turns, then the magnetic lines of force or magnetic field strength will also be n times. Because we have understood that the magnetic field produced by each turn is getting added up. If there are number of turns, n number of field strength, that is, it will be getting added up, so that the magnetic field can be increased, right? So why we are insisting on that? Because we are using this concept when you come to the electric motor. If you want a powerful electric motor, there we are going to have many number of turns. You know that you can compare that a small CPU fan and a table fan, a pedestal fan, and a very powerful fan which is used in the cinema for creating stormy weather, isn't it? So in all the fans, they are using the same kind of motor. But how the power is changing, it is because of number of turns will be more. If you are giving more number of turns, the magnetic field strength will be increased, isn't it? So that is how we can increase the magnetic field strength. And the next one, here, this is another question. Consider a circular loop. This is the circular loop, okay, which is lying on a plane of the table, or you can see plane of table or sheet or cardboard. Okay, let the current pass through the loop clockwise. What do they say? The current is passing through that clockwise. I have marked it by using an arrow mark here and another one. So it is clockwise. Okay. Now they are asking us to apply the right hand rule to find out the direction of the magnetic field inside and outside the loop. What is meant by inside and outside? The loop is here. Okay. So inside means this is inside, this is outside. You understand? So this is, the loop is going inside, the loop is coming outside. So we are asked to apply the right hand thumb rule for the inside and outside of this loop, current carrying loop, to find out the direction of the magnetic field. See that? This is the answer. What is that? We are applying the right hand thumb rule to the left side first. Okay? To the left side. So how to apply this? The current is flowing here. So keep the right hand of your thumb. Okay, this way. Since the current is this direction, I am keeping this. Say for example, say this is the table. Okay? The loop is here. The loop is coming out. The current is flowing. So I have to keep that by showing the thumb here. I am keeping that here. Now what is the curling finger showing? The curling fingers are in this direction. That means anti-clockwise. You can see that this is anti-clockwise. Okay. So the magnetic lines of force around this loop will be anti-clockwise. And similarly, when it is coming here, the current is flowing downward. That is inside. The current is flowing inward, we say. Here it is outward, here it is inward. When it is inward, what we have to do, you have to keep the right end of your thumb, that is the thumb pointing downward. So when it is pointing downward, what will happen? Similarly, when you are keeping here, you have to keep the fingers here. Now the current, the thumb is showing the direction of the current. The fingers, you see that, the curling fingers, all the 4 fingers, they are showing the direction of magnetic field in the clockwise direction. Isn't it? You have to remember that. So here it is clockwise, here it is anti-clockwise. Okay. So this is one of the question which is given in your textbook also. The next important concept is solenoid. What is that? Solenoid. A solenoid is nothing but closely wound helical coil, we say. Closely wound helical coil. Helical means like this, like a spring. Okay. Closely wound helical coil. But as per your textbook description, it will be a coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder. It is not a sire, it is wire. My spelling mistake is there, correct it. What is that? A coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder. On seeing that, can you give an example from your day-to-day life, how a solenoid will look like? You would have seen that many places. Where housewives are making use of that every day. Not a spring. Here they are saying that there are number of turns which is wound on a cylinder, cylindrical shape. Just you can compare that with one of the household article I can say. If I say that, you will say, oh, this is the one, I forgot it. This is found in the tailor shop. Tailor shop. Sewing machine, they are using that in the sewing machine. Exactly. The thread, which is wound on that. It is nothing but, if that, instead of thread, if you get a copper coil, then you can call this as a solenoid. That is nothing but a solenoid. So, solenoid is here, you can see that various types of solenoid are shown here. These are all the solenoid which we are using for various purposes. Okay. Right. Now, the solenoid, the two ends of the solenoid is going to be connected with the battery so that the current will flow through that. When the current is flowing through that, here you can understand that each one can be considered as a turn. So that number of turns are there. Many turns are there, isn't it? So, a current carrying conductor now, what will happen? It will create a magnetic field around it. So that more number of magnetic lines of forces will be created so that the whole solenoid will behave like a magnet, like a bar magnet, which has got a south pole and a north pole. But the only thing is, outside the solenoid, the magnetic field lines will be curved, but inside that there will be a straight line. When you say that the magnetic field lines are straight lines, what do you infer from that? When you see that magnetic field lines are straight, what can you infer from that? Exactly. Uniform. We say uniform field strength. The magnetic field lines, when it is straight line, at every point inside the solenoid, the magnetic field strength is same, uniform. So we call this as the inside the solenoid, the magnetic field is uniform. Okay, the field is uniform inside the solenoid. Okay, based on that, you may be asked to draw a uniform magnetic field. What will you do? What will you do? You can simply draw straight lines, isn't it? By showing straight arrow mark, that will show you the uniform magnetic field. Yeah. Here, this is the solenoid. To understand how the magnetic field is created inside the solenoid, the small experiment here. You can see that a battery is connected to the two ends of the solenoid. Here, magnetic compass is kept inside. Now, tell me, if the magnetic field is inside is uniform, in which direction the magnetic needle will point out? Can you tell me? In which direction the magnetic needle, compass needle will point out? No, which direction? Look at that. On seeing the video, you will understand. Look at that. Now look at that. Now you will understand that. Now the battery is connected. Now see that once the battery is connected, it is showing deflection, right? Once the current becomes steady, what is the direction you can see? You have to tell me one important point from this video. On seeing that, earlier the direction of magnetic field, that is the needle is like this, along the direction of this coil. Now once the current is applied, what happens? Look at that again. At the end point, when it comes here, look at that, view that. Now here the magnetic compass needle is along the direction of this coil, in the same direction, when there is no current flowing, right? So once you touch that, once you connect the battery, the current will start from 0 to maximum. At that time it will be deflecting. Once the current becomes steady, you see that, what is the direction of that compass? It becomes steady, you see. It is pointing out in one direction. What is the direction it is? Tell me. What is the direction? It should not say in terms of east or west, man. What is available in this diagram? Using that only you have to say, isn't it? We don't mention any east or west or upward, downward. We have got only a solenoid, we have got a compass. Related to these two only you have to refer. You cannot take outside. What is available here? Using this, you tell me what is the direction of the compass needle. Yes? No. How do you say that? No. How do you say that is North Pole or South Pole? How do we know? Only when the direction compass shows that, isn't it? What you have to say, what I expect from you is that the current is flowing through this, isn't it? So when it, pardon? What do you say? Yeah? Okay. See that? The current is flowing in this direction, isn't it? So I am pointing out the direction of current here. Earlier, when the current is not flowing, you can see the compass needle. What is the direction of the compass needle? It is showing like this. Okay. Now once we apply the current, steady current flowing through that, the compass needle is coming like this. So that what happens? The compass needle is showing like this. So what do you call it as? What do you call it as? Yes? Yeah, exactly. Right angle. So, yes. So, already we know the fact that when the current is flowing through that, the magnetic field will always be perpendicular to that. Even in the left hand rule, Fleming's left hand rule, you can see that all the three fingers are right angles to each other. The magnetic field and the current direction will be at right angles to each other. So that is the point you have to say. Okay, what is available here, using that you have to say. Okay. Now the next one. Now this is the question which I asked earlier. How to draw a magnetic field in a given region if it is uniform? You have to draw diagram to represent it. Right? Here you can see that there are lines here, many lines which is equidistant from each other. So this can be considered as, this uniform magnetic field can be considered as the field which is present inside the solenoid. Right? So the uniform field which is existing inside a current carrying solenoid is represented as a parallel straight lines starting from south pole to north pole. Now my question here. Earlier when you are talking about bar magnet, what is the direction of field lines? For bar magnet, what is the direction of field lines? Ah, very good. That is what I expected. You should have, when I ask question, you have to ask me whether it is inside or outside. So you have to tell me outside. But here, when you are talking about this solenoid, what I have represented south pole and north pole. Usually outside is north pole to south pole. Here when I am talking about uniform magnetic field, I have represented as S and N. In case if you represent it as N and S, what will happen? Here it is not a uniform because outside the magnet it is from north pole to south pole. But here what I have represented as uniform magnetic field is inside the current carrying solenoid, which should be south pole to north pole. Okay, opposite to the outside the magnet. Is that clear? Because the whole solenoid should be considered as a magnet. So outside the magnet will be a curved lines. So inside only it is uniform. So south pole to north pole. Because even after drawing also in the exam, if you forget to mention it is south and north, it will become invalid. So you have to remember that we are talking about the magnetic field lines inside the solenoid, current carrying solenoid, so that it is starting from south pole and terminating at the north pole, opposite to that. Right. The next one, the force on the current carrying conductor we have learnt. The magnetic field produced by current carrying conductor exerts force on a magnet placed in the vicinity of the conductor. What is that vicinity? Do you know the meaning for that word? Surrounding or the region or which is visible within that. The magnetic field will be experienced or exerted by this rod which is carrying current. So within that vicinity only the magnet should be kept. So if it is kept within the vicinity, what will happen? It will exert a force on the current carrying conductor. And who proposed this theory? Do you remember that? Who gave this theory? Exactly. Andre Marie Ampere suggested. He only suggested that based on the Newton's third law, equal and opposite force. Right? When the magnet is exerting a force on the, that is when the rod is exerting a force on the magnet will also exert the force on the current carrying conductor. This was suggested by him. Okay. Now, based on that experiment, we have understood that the direction of force of the conductor depend on two important factors. One is the direction of current and the second one is the magnetic field. What is that? If the direction of the current is changed, the rod will deflect in one side. Right? If it is reverse, what will happen? The rod will deflect on the other side. Right? And similarly, the displacement of the rod is largest and the direction of current is at right angles to each other. Because sometimes this question will be put like this. In the following diagrams, given diagrams, in which diagram you would think that the displacement of the rod would be maximum. They may give that as first one at 30 degree, 40 degree or 90 degree. You can say that exactly it is when it is right angles to the direction of the magnetic field, the displacement will be maximum. Now you come back to this video. Just compare this one with that video. Right? when the current is flowing through the solenoid, right? And the displacement, you can see that the magnet is showing at right angles. So the magnet is displaced because the magnetic compass needle is a magnet, isn't it? So that magnet is experiencing a force due to the current which is flowing in the solenoid. Now, when the current is flowing at right angles, what happens? The deflection is maximum. When it is at 90 degree, it is turning again at 90 degree. So you can compare that with this one. So we understand that the displacement will be largest when the current is flowing at right angles to that. And I hope that you remember this Fleming's left hand rule. Yes or no? Yes? Can you repeat it without looking at that board? Can you repeat it now? State Fleming's left hand rule. Yeah, repeat. Oh my God, you have changed that slide, sir. How can I repeat it now? Do you say that? Yeah. Exactly. Come on. No, you have left one important point of your which hand, right hand or left hand? Yeah, because we are going to learn another rule, right hand rule also, which is for yes, that is very important. If you leave that word left hand, the word will, that is the definition will become meaningless. So stretch the first three fingers, thumb, forefinger and middle finger of your left hand such that they are mutually perpendicular to each other. They are mutually perpendicular to each other. Then, now if then condition. If like this, that's all. Exactly. See that's all. If you apply that, easily you can remember that. Very good. Okay, you need not study at all. Okay, this is what we call it as learning. Instead of reading, if you learn it, at any time you can just reproduce it without looking at the textbook. Good. Now, here there are some devices that use the current carrying conductor and magnetic fields which are related, no? Using that, all these components, all these devices are working. There may be some question which is based on the examples. Give examples for devices which work on the magnetic field, current carrying conductors and the magnetic fields. Okay, so these are there. What are they? There is electric motor here, and generator is here, and then you can see the loudspeakers, microphone, and the electric measuring devices. In all these components, I would say that you got a speedometer, odometer and speedometer, and on the bike also. That speedometer is also working on the same condition only. The disc brake is there, no? The disc brake is also based on this only. When you are applying the brake, you are applying the current. So due to this current, it is creating a magnetic field. So when this magnetic field is created, the disc is rotating inside, no? That will suddenly stop. Okay, that regarding that you will study in the higher classes at probably in 12th standard. Okay, so most of the devices which are working on the relativity between this current carrying conductor and the magnetic field, which is very interesting concept. Okay, so these are the examples. By looking at the pictures, you can easily remember. Okay, so the next question is one of the interesting question you can see. This is relating the previous chapter also. Okay, an electron entering a magnetic field at right angles to it, as shown in the diagram. Find the direction of force acting on the electron. Find the direction of the force. So simply we will say that we are going to apply Fleming's left hand rule and find out the direction of the force acting on the electron. But what is the question here? They have not given the direction of current. They have not given the direction of current. Is that the direction of current given here? See, 3 points we need. If you want to find out the force on the conductor, we need the direction of magnetic field and direction of current. But is the direction of current given? If the direction of current is not given, how will you find out? Then how will you find out? This direction shows only the direction of flow of electron only. The electron is entering the field. But that cannot be taken as the direction of current. Exactly, good. So, what we have to do, we have to interpret the diagram like this. So, this is the diagram given here, the direction of electron and the magnetic field. And you have to assume that the convention method is, this electricity lesson you have learnt, the direction of current is always taken as the opposite of the direction of movement of electrons. So when the electron is entering this direction, we have to take the current in this direction. So now we have got the direction of magnetic field is here, current is here. Now apply the left hand rule, Fleming's left hand rule. What you have to do, keep the finger like this. This is the magnetic field. The fourth finger shows the magnetic field, and this is the current. Yes? What will happen? In which direction? How will you keep the finger now? The current should be in the opposite direction. Now this is how we have to keep. See, I am keeping by keeping my thumb towards the board. You can see that. So this is the direction of magnetic field, and this is the direction of current. Now that my thumb is pointing towards the board. Towards the board means when you are writing the examination, you would say that it is directed into the page. Do you understand? Are you able to see my hand? Yeah? Do you understand that? Yeah. You can just when you are writing the exam also, if the paper is here, when you are writing here, you just have to hold like this and keep the finger and see. See? You have to keep the finger and see. Okay? So this is the direction of magnetic field, and this is the direction of current. Now the thumb is going inside the page. So the answer should be into the page. Directed into the page. Okay? Right. The next one. Which of the following property of a proton can change while it moves freely in a magnetic field? Remember that we know that when an electron is, that is current, flow of current is nothing but the flow of charges, isn't it? So the electrons are flowing. Otherwise we can say the current is flowing. Now they say that they have taken a proton. Instead of electron, they have taken proton, which is also a charge. So the charge is allowed to move freely. That is, which property of this? There are 4 properties that are given: mass, speed, velocity, and momentum. Okay, among these 4, which will change? They are asking. Actually, we know that when electron is flowing, when the current is flowing, it will experience a force, isn't it? It is exerting because the magnetic field will be created. It will experience a force, isn't it? So that what will happen, due to which the velocity will change. When the velocity is changing, which property is related to velocity here? Can you tell me among these 4, which property is related to velocity? No, which property is related to velocity here? Velocity we know. Among these 3, which is related to velocity? And why? Can you tell me the formula for momentum? Do you remember that? Exactly, mass into velocity. So that is why we say that both this velocity and the momentum will change. P is equal to mv, we know, momentum. So once the velocity changes, why the velocity is changing? Because the magnetic field is exerting a force. Due to that force, speed won't change. Why? Because I am not taking into account, because Here whatever property we say here, everything is vector. The velocity, in which direction the current is flowing, we are mentioning the direction in which the electron is flowing, isn't it? So once we are mentioning the direction, we cannot take the speed. Speed is a scalar quantity, so we cannot take into account. Mass is not coming into account because the mass will not change. Do you think that the mass will never change when it is entering the field? The mass of the electron when it is entering the field, magnetic field, do you think that it will change? It cannot change actually, isn't it? At 10th standard level you would say that it will not change. But as you proceed further to higher classes, you would see that mass will also change. But as per your syllabus, we say that it will not change. Okay. But this is the concept which is given by our great scientist, Einstein, Albert Einstein. He only gave the relativistic variation of mass with velocity. What did he say? For example, if I take a chalk piece and throw on you, do you think that will hurt you? A small piece of chalk. No. Instead, you would have seen that your friends playing inside the classroom. Yeah, exactly. But if I hold the same chalk piece using a rubber band, okay, by tying that with the rubber band and point you and just throw it on you, what will happen? Wow, hurts a little more, isn't it? Yes or no? Why? 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 Chalk piece is increasing. So we understand that when the velocity is increasing, it momentum is increasing, isn't it? Momentum is increasing. Similarly, Einstein said that this small chalk piece is sufficient enough to break even the whole earth under one condition: if it travels with the velocity of light. If the same piece of chalk travels with velocity of light, that is sufficient to break the earth. That means he says that the small chalk piece will assume infinite mass. 1 gram chalk piece will assume infinite mass if it travels with the velocity of light. But so far, nothing can achieve the velocity of light. That is why it is not happening. Okay, so those things you will be studying in higher classes like 12th standard when you are talking about the different instrument for accelerating the particles. We call it as cyclotron, betatron. Okay, cyclotron is the device which is used for accelerating the charges. There you would see that the same electron or proton, that is proton, will be varying in the mass. But at present we say that we are not taking into account these two. Only the two things which will be varying is velocity and momentum. Okay. Right. There is another question. Shall we proceed or we will take in another class? Because I have taken more time. Yeah, just for 5 or 10 minutes more. Okay, I will complete this. So there is a diagram given here, right? How do you think that the displacement rod, the displacement of a rod AB will be affected? There are three conditions they have given. Okay, this is the diagram given, and they are asking the displacement of the rod AB will be affected. How it will be affected? But under these three conditions. One is the current in the rod AB is increased. The second one, if a powerful horseshoe magnet is used. The third one, if you increase the length of the rod. These are the three conditions. Right? Can you assume what would be the result of these three? Let us check it out whether you are able to give the correct answer. Tell me the first one. If the current in the rod AB is increased, what will happen to the displacement of the rod? And why? affected, will it be more or less? Why? It is actually, you have to say the point that if more current is there, it will produce more magnetic field. The field strength will be increased, isn't it? So that due to that, what will happen? The force will also be more, so that it is displaced more. Exactly, very good. If instead of that ordinary horseshoe magnet, if you are using a strong horseshoe magnet, what will happen? Second condition. More. Yes. So that the force exerted by this magnet on this rod will also be more. Since magnetic field is more, it will exert more force on the rod, so the rod will get displaced more than the previous one. The last one, the length of the rod AB is increased. Again the same condition. Third point is also similar to that. In all the three, we can say that the displacement of the rod will be more. Okay. So the point you have to remember that the more force here, the first point you have to remember, more force will be acting on the rod when the current is increased. Second one, what will happen? It is leading to a greater force because the magnetic field strength is more. So it is exactly because more number of electrons will be flowing inside the rod, isn't it? For a long, the length is more means for a longer distance the charges are flowing. That means it is carrying more current, isn't it? So more charges are accumulated within the distance. So that due to that it will produce more amount of force. So that will get displaced because of the interaction. Exactly. Okay. And similarly in the third one also, when it is increased because of the more number of charges, it is creating more magnetic field. So it will experience more force, and the interaction between this will also be more. So it gets displaced more. So for all the three, the point is that the rod will experience more displacement. Right? Okay. Shall we start with this one? We've got more number of questions. Okay. You tell me when shall we have the next class? In the next class, we'll take the remaining part of that. I hope that before 18th or 19th, we'll be able to complete this lesson. Okay. And I'm happy that you are able to give nice answers. That shows that you have understood the lesson properly. Good. Keep it up. See you in the next class. Thank you.